Let's now consider antiviral drug resistance and hepatitis B. What I've shown on the next slide are the primary resistance substitutions that we see for the 5 approved therapies in chronic hepatitis B. Here we have the L-nucleosides lamivudine and tolbibudine, acyclic phosphonates, adefovir and tenofovir, and the D-cyclopentane and entecavir. And I've stylized the HBV polymerase as a linear diagram with the polymerase RT molecule region shown for you in blue. The L-nucleoside resistance is associated with the RT-M204V or I substitution. This is the old YMDD resistant variant described in the literature. The minor pathway that we see for the L-nucleosides in terms of resistance is the RTA181T or V. Now the acyclic phosphonates, adefovir, tenofovir, resistance is associated with the RTN236T with or without the RTA181T and V. For D-cyclopentane and entecavir, at least 3 substitutions are required. The RTL180M plus the RTM204VI that we see typically with lamivudine, tolbibudine, the L-nucleoside group, plus one of the 169, a 184, a 202 or a 250 substitution. Now these 9 primary resistance substitutions have been classified into 5 pathways of drug resistance in chronic hepatitis B. The first pathway is the L-nucleoside pathway, typically identified by the mutation RT-M204V or I. The acyclic phosphonate pathway, RT-N236T. The shared pathway, as I pointed out, is the RTA181T or V that is shared between the acyclic phosphonates or the L-nucleosides. In patients who start entecavir in a naive situation, the naive entecavir resistance pathway is the RTL180M plus the M204V or I with one of the 169, the 184, the 202 or the 250. In recent times we're seeing more of the multi-drug resistant pathways where patients switch from one pathway to another, and complex patterns such as RTA181T plus the N236T or the M250L are being identified, and we call this a multi-drug resistant pathway. The second group of substitutions I want to talk about are the compensatory mutations. On this graph I've plotted the relative replication yield of particular hepatitis B variants and that pattern of the number of mutations or the pattern of mutations associated with those particular isolates. I draw your attention to the red arrow, which is boxed as the wild type drug-sensitive hepatitis B virus reference clone, and I've ranked that as a number 1. Now the common lamivudine resistant substitution is the L180M plus the M204V directly underneath that wild type reference clone, and that you can see there's a 30% reduction in the amount of replication associated with that variant. Now if we just add V173L and go straight to the top of that figure, as you can see in that blue bar, we've now increased the replication yield 8-fold compared to the wild type reference clone and almost 15-fold compared to the lamivudine resistant L180 plus the M204V. So the V173L plus the 180M plus the M204V is a common lamivudine resistant variant with a compensatory mutation at V173L. Now this leads into the situation of the multi-drug resistance problem. This is the sequential addition of resistance mutations to the same viral genome. This is promoted with sequential monotherapy, especially by using drugs with similar structural characteristics like using L-nucleosides one after the other. The role of compensatory mutations really do promote replication yield, and as we just saw with the V173L, and therefore this complicates for the physician the profile that we see in terms of the genetic variants that are found in the infected individual that is failing their therapy. And there is a need for drug resistance testing, the polymerase sequencing, in order to determine and choose the best therapy to go forward. So for example, is it an RTA181T that is actually selected out on lamivudine, and then when we added adefovir back, the patient failed to respond, then we can understand that through that shared pathway, that would be the outcome for that particular individual. And neither lamivudine nor adefovir are appropriate treatments. If the sequence showed a 181T plus the N236T and the patient was switched to tenofovir, then we would get a blunted response there as well, because they are shared resistance pathways. For the 181T plus the I233V plus the RT-N236T plus the RT-M250L, this is a complex multi-drug resistance pathway, then none of the 5 approved treatments are active against that particular group. So when we put all of this into context, it can almost predict in a reliable way where our patients will be in 1 year, 3 years, and in 5 years' time if you put patients on particular nucleotide analogues. So we know with lamivudine, for example, that after 1 year, almost 25%, and by year 2, almost 50%, and by years 3, 4, and 5, to 80% of the patients are now resistant to lamivudine. For adefovir, 0 by year 1, but 3%, 11%, 18%, and almost 30% by year 5. For tolbivudine, 5% for year 1, but rapidly accelerating to 25% for year 2. For entecavir, we have very good data where it's less than 1% for the first 3 years, and then after that time, no new resistance emerges after year 3. Bristol Myers have resistance data out to year 6, and that's very convincing that by year 6, only 1% of the population of treated patients will be resistant to entecavir. For tenofovir, we have good data to week 72. It's 0% for antiviral resistance. And for patients who were non-viremic by week 72, even after 3 years, they are still, there's been no evidence of tenofovir resistance in naive patients.